Hello, I am Chiamaka Ibeanusi, and this is my Physics Lab 1 report. In this lab, I tracked the motion of a body and created the computational model of the same experiment that predicts that motion. The purpose of this lab is to use our knowledge of Newton's second law to predict the motion of a body moving with constant velocity. The model's predictions are quite accurate because, as you will see on the graph of my results, the motion of the object in the model is almost exactly the motion of it in the experiment. The formulas here are derivations of Newton's second law, the momentum principle, which were very useful in the creation of my computational model. This law was used because the formula enables us to predict the future movement of a body with constant velocity, which in this case is a ball. Some assumptions were made during the experiments. For one, the net force on the object is zero. Friction is negligible because the ball was rolled on a smooth table. And air resistance is negligible as well because the experiment took place indoors with no fans on and the windows were closed. For this experiment, I observed the movement of a small ball across a smooth desk from left to right. The ball in this case is the system, while everything else in the environment and universe, including the table that the ball is directly in contact with, is the surroundings. The mass of the ball is 0.04 kilograms and the diameter of the ball is 0.07 meters. The video was tracked a few seconds after the ball was initially pushed to ensure that the velocity was constant and was stopped a few seconds before the ball fell off the table. I indicated the diameter of the ball and tracked the ball at each time frame to observe its motion. This can be seen in the following video. The data from the tracker shows that the graph of the position against time is a positive linear graph, as seen here. To code the computational model, I used the GlowScript starter code that was provided. The code in the image affects the visual representation of the ball, so I did not edit anything here. In this section of the code, I changed the mass of the ball as seen on line 32, the initial position as seen on line 35, the initial time, which is 0 seconds, as seen on line 39, and calculated the initial velocity using the formula to the right as seen on line 36. The delta t should be small for a more accurate prediction, thus it was 0.01 seconds. For the loop, I used my total time of motion as a breakpoint. There is no net force as mentioned before. We can also see that the formulas from earlier for predicting future velocity and positions from Newton's second law are on lines 58 and 60. Because the velocity is constant, the average velocity is equal to the final velocity, as seen on line 60. When the program is run, the following are the results. Finally, I graphed the position of the ball in my experiment and the position in the computational model. As you can see from the graph, the motion of the ball in both models is almost identical. This shows that the use of Newton's second law to predict the motion of an object is accurate. You may notice that both graphs are linear due to the constant velocities, and the same time frames are used for both the experimental and computational models. There are very slight differences between these two, which may be caused by the camera angles, which could affect the perception of motion, and the external forces, such as air resistance, that we neglected, and slight friction. This means that the net force for the experiment is not exactly zero, but that of the computational model is. There are some questions that we may ask ourselves after performing this experiment. This graph shows that the graph of the model would look like if the orientation of the axes were different. That is, if I decided to create the graph in the second, third, or fourth quadrants instead of the first. I think the magnitude of the velocities would be the same in all, but the direction would change depending on the quadrant chosen. For this question, we are asked whether it is possible to say how many forces are added together to give the zero net force in the case that we observed. I do not think there is a way to measure all the forces acting on the ball in this case, mostly because only changes in position and time were measured, meaning we cannot calculate the forces with the data that we have. Thank you for listening, and I hope you learned something new.